Okay. Now question number 3. Iron is a transition metal in group 8 of the periodic table. Explain why iron has a variable oxidation state. So, if the transition metals, if you recall why they have a variable oxidation state, it is because the 3D and 4s subshells energy levels has very small difference, and as they have a very small difference, so the transition from the electron can be lost from either of them, so that's why it forms a variable oxidation. It has a variable oxidation state. Complete the shorthand electronic configuration of iron and iron 3 positive. Okay, so if you recall the atomic number of iron, if I think iron is 26, so which means as an iron atom it has a 26 electrons, and when it becomes Fe3 positive, so 26 minus 3 makes it 23 electrons. So remember, first electrons remove from 4s and then 3d. Okay, now have a look at the periodic table. No. Yes. So, yeah, it's 26, right? And the other thing, they have been started from argon. So till argon, we have 18 electrons and it's third period. So it means that from here, it's 3p6. So we are filled with 3p6. So we have to just fill 4s and 3d. So 18 electrons are over here. Now after 18, there are 26. So how many are left? 8 electrons are left. So in 4s, we get 2 electrons. Sorry. Yeah. In 4s, we got 2 electrons. Now how many electrons are left? 6 electrons are left. So we are going to fill those 6 electrons in 3D. So either you can write it like this or you can write it like this, 4s2 3d6. Both are correct. But remember, first electrons filled in 4s and then the electrons are filled in 3d. Now, if it's 3 positive, so 3 electrons are removed. So 2 electrons from 4s and 1 electron from 3d. So it is going to be 3d5 only. Is this clear to all of you? Okay. Now, B part. An aqueous solution of iron 3 nitrate contains the complex hexaaqua iron 3. Okay, iron. When the solution of KSCN aqueous and hexaaqua iron 3 are mixed, a color change is observed. The red complex is formed. Define a complex. So you have to remember the complex, the definition of a complex. We can define it as a molecule or ion in which a metal ion is surrounded by a ligand. Is this clear? Okay. Now, 2. State the coordination number of iron in hexa-aqua iron complex. So if you see, there are 6 water molecules, and water is a monodentate ligand. So one water forms one dative bond. So 6 water molecules form 6 dative bonds. So the coordination number is 6. Is this clear to all of you? Now, third part. The HOH bond angle in water is 104.5. Suggest the bond angle in FeH2O6 3 positive. Okay, now this is an interesting question or an interesting part, because if you see the iron, it is like this, and with this the oxygen bonded over here. Now if you see, when the oxygen bonded over here, now this oxygen has a one lone pair left. If you recall the water molecule over here, it has a 2 lone pair and 2 bond pair, right? 2 bond pairs and 2 lone pairs, which makes the bond angle of 104.5. Now, if you see over here, this oxygen has a 3 bond pair and 1 lone pair. So when this is the case, that there are 3 bond pair and 1 lone pair, the bond angle is going to be 107 degrees. No, not 120. 120 is as if when there are only 3 bond pairs and no lone pair. Okay. So over here, uh, the bond angle is 107 degrees. And why it is 1 lone pair of oxygen is shared to form 1 minute. Okay. Is shared to form a dative bond oxygen has 1 lone pair and 2 bond pairs. Hence, the repulsion between lone pair and bond pair decreased. So that's why the bond angle is increased from 104.5 to 107 degrees. It's 104 when there are 2 bond pairs, and now there is a 1 lone pair and 3 bond pair. So due to which it goes to 107 degrees. Is this clear? Just give me a minute, please. Yes. Okay, we started from here, Mariam. One minute, Mahveen. Yeah, sorry, it's two, not two bond pairs, it's three bond pairs. Yes. Okay. So till here, is this clear to all of you? Okay. Now part 4. Explain why iron complexes are colored. So as we know that in complex, the d orbitals is split into two energy levels, right? One goes to the higher energy and the other group goes to the lower energy. Then electron from lower energy jumps to higher energy by absorbing light energy. Hence, the color is seen is the complementary color of the color absorbed. Is this understandable? Now part 5. Aqueous solutions of complexes hexaaqua iron 3 and are different colors. Explain why these complexes are different colors. Okay. So the reason behind is, see, both have a different ligands, right? So here what will happen that the energy difference between two set of d orbitals differ due to different ligands. Hence, wavelength, or you can write different frequency of light is absorbed by each complex, and that's why they are observing the different frequency of light, so they are transmitting the different frequencies, and as a result the color which is shown, the color which is absorbed is different, and the complementary color which is shown is different. Is this clear to all of you? Now see, table 3.1 gives values for the stability constant of a different complexes of iron. Okay. So if you see, this one has a 5.90 exponent 1 and exponent 2. Okay. So it means between these, this is more stable, right? Because its K stability value is higher. And these K stability values are relative to the hexaaqua complex. Okay. So part 1 can form when phosphoric acid reacts with this. Write an equation for this reaction. Okay, so it's very simple, because if you see, they are telling you that phosphoric acid H3PO4 is reacting with this hexaqua complex. So I will write it over here and then H3PO4, right? And then over here Fe, and I will write this complex H2O5, H2PO4. So see, it's H3PO4, now it becomes H2PO4, right? So one hydrogen ion is released and one water is released. So hydrogen ion and water joins with each other forming H3O positive. See, from here one water is released and from here one hydrogen is released. So they will form H3O positive. And if you see, the equation is balanced. Is this clear to all of you? Now, K step expression. What they are saying, write an expression for K step of this complex and give its unit. Okay. So as you, okay, there is no water over here. So the expression will be, but there is a one water which is being released from the ligand, and I have told you that the waters which are released will not be written in the expression. Okay. So in the numerator we have a react product. So the product is FeH2O5 and H2PO4 and then 2 positive. So I will enclose it in the square bracket for the concentration. And see, it's the water ligand which is released from here and which accepts the hydrogen ion. And I have told you, in K stability expression, we don't write that water. So that's why I'm going to skip this one as well. And I'm not going to mention it in the K step expression. Okay. Now, in the denominator, we are going to get this complex, the hexaqua complex, FeH2O6, 3 positive, and enclose in the square bracket, times H3PO4. Okay. Now, each one has a 1 mole, so there is no need to put any power. Now, if I work for the unit, so mole per dm cube in the numerator over mole per dm cube in the denominator times mole per dm cube in the denominator, right? So 1 unit from the denominator is cancelled by the numerator, and the rest one moves to the when numerator, it will become mole inverse dm cube. Is this clear to all of you? Okay, I've used this one to write the expression, but here they are saying this one. Thank you, Miriam. Yeah. So if I'm using this one, so here SCN is must be used as, so sorry, over here. So we are going to get a SCN over here in the complex, and here we are going to get a SCN negative, which is the ligand. Yeah. Okay, I've thought that they are asking for the case step expression for this one. So that's why I've used these terms. So instead of this, it's SCN and SCN negative. So this whole complex is going to be over here. So it's basically like this. Instead of this H3 positive, you are going to use SCN negative. And as a result, you will get a SCN over here and there will be nothing over here. So if you will write the case step expression, it would be like this. Is this clear to all of you? Yes, is it clear now? Yes. If any one of you has any confusion, please ask. Okay, third. Use the stability constant at n table 3.1 to calculate the value of the equilibrium constant Kc for the following equation. Okay. So if you look over here in this, if I'll make the Kc expression out of this, then it would be FeH2O5 SCN2 positive over and square bracket times H2PO4 negative divided by FeH2O5 H2PO4 2 positive and then SCN. So how we will use the table? Because if you see over here, it's the K step value of this complex. And if it's the K step value of this complex, so sorry, so this complex is in the numerator, right? And if you see over here, this complex is also in the numerator over here. So it means basically this Kc, the Kc of this equation actually is Kc is equals to, if I say this one a K step 1 and this one a K step 2, so this one, this complex, if you see over here is in the numerator. So it is going to be 2 divided by 1. 2 is this and 1 is this. Why is it so? Because this complex is in the numerator of this equation. So it is going to be in the numerator, its value. And the other complex is in the denominator of this equation. So the K step value of the other complex is going to be in the denominator. Is this understandable? Just give me a minute, please. Okay, now have a look over here. This complex value is this. And if you see, this complex is in the numerator over here, right? And this complex is in the denominator over here. Is this understandable? Is this understandable? So when we are going to put the values of K stability, the complex which is in the numerator, we are going to put its value in the numerator, and the complex which is in the denominator, we are going to put its value in the denominator only. Because see these complexes position over here. So if I'm going to put the values, so it is going to be 1.30 exponent 2 over 5.90 exponent 1. Is this clear? Okay. So if we calculate the value, we will get the answer. Okay, 2.203. So if anyone of you has any confusion in this, please ask. Okay. So the answer is 2.203. Okay. Now we are going to start with question number 1. Sorry, question number 4. Just give me 2 minutes, please. Okay. So yeah, let's start with question number 4. Sorry. Ruthenium and osmium are transition metals below iron in group 8 of the periodic table. Okay. Two different complexes, ions X and Y, can form when anhydrous ruthenium chloride 3 chloride reacts with water under certain conditions. Okay. X and Y have a octahedral geometry. Aqueous samples of X and Y react separately with an excess of silver nitrate. Different amounts of AgCl are precipitated. Okay, so it means that each one have a different amount of chloride in it. Okay, 1 mole of complex ion X produces 2 moles of silver chloride, and 1 mole of complex ion Y produces 1 mole of silver chloride. So it is the formula of X and Y. Okay, so remember that the halogen as ligand would not precipitate. So that is very important thing. So in actual, how many chloride are there? 3 chlorides are there, and in the complex X we are getting 2 moles of chloride. So it means that over here, that when the complex form, in that complex there are going to be, uh, 5 water molecules as a ligand, 1 chloride as a ligand. So as a result, we will get a 2 positive ion, because see over here, if you see, it's -1 times 3 and the net charge is 0, which makes ruthenium +3. So if there is a 1 chloride which makes ruthenium is 3 positive and chloride is -1. So that's why the net charge is 2 positive. So that's indicates that there are 2 chlorides which are actually bonded ionically over here. So you can write the formula like this, or you can write the formula like this. Both are going to be considered as a correct. Just this and put up 2 positive charge. My screen is again stuck. Yeah, it's clear now. Now, here we are getting 1 mole of a chloride. So which means that now there are going to be, out of 6, 4 water molecules, 2 chloride ions are the ligand, so that are not going to be precipitate out. So 1 chloride ion forming an ionic bond with this complex ion, and that is going to be precipitated out. So you will write this, the formula, or you are going to write the formula like this, just a complex ion with no spectator ion. So here it has a +1 charge. Is this understandable to all of you? Yes, if anyone of you has any confusion, please ask. Okay. Now part 2. Both complexes react with an excess of bipyridine, BIPY bipi, to form a mixture of 2 stereoisomers. Okay. See, it's a bidentate ligands, and there are 3 bidentate ligands, right? Bipyridine is a bidentate ligand, they have told you. Draw 3-dimensional diagram of a 2 stereoisomers. When there are 3 bidentate ligands, then remember that it's always an optical isomer, and optical isomers are drawn by making the mirror images. So see how I'm going to draw it. We know 2 bonds are going to be below the plane. 2 bonds are going to be above the plane. So I'm going to do this on both sides. Now see how I will make the 2 mirror images. So they told you that you have to draw pi like this. See, initially 6 water molecules are formed in the complex, right? So when we are getting 1 mole of silver chloride, so it means 1 chloride ion is there, which is going to precipitate out, and 2 chloride ions are going to be in a ligand. See, there are 3 chlorides. So out of these 3, 2 becomes ligand and 1 stays over here. So when 2 becomes 2 chloride attaches over here, so what 4 water molecules must be there out of 6. And as 1 chloride forms a ligand, so 5 water molecules are going to be there out of 6. Is it clear, Mahveen? Okay, now we have to show this structure, the 2 mirror images. So I will put if one over here, so I'm going to exactly put opposite to it to show the mirror image. If I put one bidentate ligand like this, so over here I'm going to put one bidentate ligand like this. And if I put one bidentate ligand like this, so I'm going to put the third one bidentate ligand like this. So it will form a mirror image. Is this clear to all of you? Okay. Now B part. Figure 4.1 show another ruthenium complex. Okay. This complex contains a neutral ligand pyrazine. Okay. So here there is a one ruthenium and here there is another ruthenium. So just how pyrazine is able to bond to 2 separate ruthenium ions. So if you see, it's due to the dative bond only, because when it's a ligand always forms a dative bond, right? And dative bond is formed because it has a lone pair of electron with it. So we can write over here that nitrogen has one lone pair of electron. And see, there are 2 nitrogens, right? So each nitrogen, and that's why each nitrogen is forming a dative bond with the one metal. So each nitrogen has one lone pair of electron, and each nitrogen atom share its lone pair to form a dative bond with transition metal ion. Is this understandable to all of you? Okay. Now part 2. Pyrazine is an aromatic compound. The bonding and the structure of pyrazine is similar to that of benzene. Describe and explain the shape of pyrazine. In your answer include hybridization of nitrogen and carbon atoms. The orbital overlaps form sigma bond, form pi bonds between the atoms in the ring. So it's very easy. See, if you see there is a pi system. So the shape, first I'm going to discuss the shape. So the shape is hexagonal, right? Because it's a hexagon, right? Hexagonal ring, which is planar, right? Because due to the pi bonds, all atoms are going to be on a plane. And if you see carbon and nitrogen, each one is involved in the bonding, right? Each one has a involved in the pi bonding. The whole ring in between shows that each one is involved in the pi bonding. So it means that this thing, hybridization, the second thing, both carbon and nitrogen atoms are, because there is a one pi bond, so the hybridization is going to be sp2, are sp2 hybridized. Okay. Now, orbital overlapping forms pi bond. So, third thing, pi bond are always, p orbitals always involved in pi bonding, and they overlaps in a sideways fashion, right? So, p orbital from each atom overlaps in a sideways fashion, is this understandable to all of you? So we are done with all three things which they have been asked. Okay. Now, third part. Predict the number of peaks seen in carbon-13 NMR spectrum. Okay. Of pyrazine. So it is going to show us a carbon's environment. So if you look over here, there are 4 carbons. But what about their environment? If I see this, and this, there are 4 carbon atoms. What do you think about their environment? Aren't they have a same environment? Because on one side, each carbon is bonded to a carbon, and the other side, each carbon atom is bonded to a nitrogen, and each carbon's p orbital is involved in hybridization. So if you see over here, all carbon have same environment. So it means how many peaks we are going to get? We are going to get one single peak for all 4 carbon atoms, right? So one peak only, as all the carbon atoms have same environment. Now fourth part. The overall charge of ruthenium complex in figure 4.1 is +5. Reduce the possible oxidation number of 2 ruthenium ions in the complex. Okay. So it's 0. It's 0. It's 0. Right? Because ammonia is 0 and pyrazine is shown over here, it's 0. So there are 2 possibilities. It's +5. So we get a +5 over here when one is +2 and the other one is +3. Or the first one is +3 or the second one is +2. Or if it's +1 or it's +4. So that's how we are going to get the +5 charge, because it's the transition metal ion, and transition metal ion loses the metals. These are the metals. So when metals loses the electron, so they have a oxidation number in whole number only. So it means one is +2 and the other one is +3. Is this clear to all of you? Okay. Now, osmium tetraoxide reacts with alkenes in a similar manner to cold dilute acidified manganate. Figure 4.2 show a proposed synthesis of condensation of polymer G. Okay. So see, the carboxylic acid turns into acid chlorides, and here an alkene with the osmium oxide is converted into an alcohol, obviously, because here we have an acid chloride and here we have oxygen. So carboxylic acid or alcohol goes condensation polymerization, or acid chloride and alcohol goes condensation polymerization. So just a reagent in step 1. So OH is turning into Cl. So I think you can use PCl5 at room temperature, SOCl2 at room temperature, or PCl3 with heat. So you can write PCl5 or the other two. Is this clear to all of you? Now, next part, draw the structure of exactly one repeat unit of a condensation polymer of G. The ester linkage should be shown fully displayed. Okay, so let's start with this one. Let me draw this one first and then this one second. So if I draw the first one, and here we got a C double bond O, and here we got a C double bond O. Cl is going to be removed from both the sides because we have to show the one repeat unit for condensation polymer. Till here, is this understandable to all of you? Okay, now it's C6H12O2, right? So it means, let's suppose CH2. Okay, and see, if we are by reacting this, there is a double bond, so it's highly mean that this structure would be this only, OH and OH. Now see, you are, if you work for its molecular formula, it is going to be C6H12O2. Is this clear? So from the OH, H is being released and O is going to bond over here. When O is going to bond over here, the whole structure comes like this, and the other O, and then the empty bond. So that's how we got the repeat unit. Is this understandable to all of you? Okay. So we are left with the two questions that we are going to end in our next class, that will be tomorrow, inshallah. So see you everyone in the next class. Take care. Goodbye and Allah Hafiz.